I would like to begin by putting together these 4-bit inputs for our comparator device, both of them, X and Y. So let's first create a label, and this will be our 4-bit magnitude comparator right here. And just put it in. Okay, and of course this is laboratory 5, which we can also add to our annotation. Like this. Okay, so let's get started. So I'll just start with inputs X and Y. And if you Control C and Control V, you can just add more of these devices for individual bits and align them, and then we'll just copy select them, and I press Control C and Control V to copy them. So now we have potentially 2 of them, and of course we'll label them input X, and again duplicate this, and this will be our input Y right here. And it is always a good idea to save your work, and we can save it as Lab 5. Name it 4-bit magnitude comparator. Okay, this works. So then of course we're going to use, as we discussed right here, so we need a 4-bit adder, and we'll supply X plus not Y to that adder to begin with. So I am now going to open Part Center right here inside Digital Works, and under macros we need this 4-bit binary adder macro to use in our circuit. So I think once you select it here, you can drag and drop, and yeah, so this is exactly what we need. So we need to supply X, and we need to supply Y as inputs B and A, doesn't matter which side. And we're gonna start looking at the carry output for this indication of X greater than Y. So of course here we can now close the part center, and now let's use the NOT gate or the inverter to produce a complement variation of the Y input. So we can use 4 of these devices. I'll just rearrange them to stay like this. Control C and Control V. We can place them quite next to each other like this, and we need 4 of them. So let's give it a little bit more space, like this. It's nice to be able to select multiple items over here, and so this will be input Y that we're going to invert. Okay, so I'll just go directly to wiring tool and make these connections. So we just attach these inputs, and of course now it goes into the right hand side of our adder. And the input X is going directly to the set of inputs for B bits right here. So that we'll be able to add these values. and we need an LED indicator for carry out to kind of like nicely indicate the condition when x is greater than y. Alright, so once we have this, we can of course make another connection. Arrange everything like this, and we can even start doing some testing. So remember, this is magnitudes which are always positive or zero. So let's first of all let's save it and put it into simulation mode like this, and using our object interaction tool, we can say that if x is greater than y like this, you see that we immediately begin to get some results right here. So when x is staying greater than y, it looks pretty reasonable, and it's still greater than y, and it's still greater than y because I'm just changing lower bits over here, and it's still greater than y because we still have the higher bit set. But now y became larger magnitude, and the carry flag is reset. So when they're the same, you see that when they're the same, it's not lit, so which is a very nice outcome so far. Or if this becomes less, we still get the correct indication. It's not true that x is greater than y right now, but if y becomes smaller number, immediately we get our result. So what about the other case? Let's stop the simulation and try the opposite case. I suppose we can also think about this. And so the opposite case would be when x is less than y. Well, you can imagine that we can just do y plus not x, and that should indicate that y is greater than x, or x less than y, whichever way you spell it. So I think that we can just produce sort of like a mirror image of what we have. Let's just adjust positions of some of our circuits, so that's nice to have next to each other because they're working really close together. Perhaps this as well. Okay, and what I'm going to do is I'm going to select the lower part right here, press Ctrl C and press Ctrl V to simply duplicate what we had over here, and this will be hopefully the opposite result. And for symmetry reasons, just for the reasons of clarity, we'll just connect the x to the other side and connect y directly to this side. Or to maintain symmetry, we could just maybe delete these connections between the inverters and move them to the other side, but it really doesn't matter. The adder will work the same way whichever way we do it. So I guess for now I just keep it the way it is and just make these connections to the opposite side. Of course, just be careful not to misplace the wires, because we need to follow very precisely the positions of bits and the way they correspond to our connections. So I guess this is good enough to maintain the order and keep everything as straightforward as possible. And here again, the lower bit of the second input should go somewhere into the lower and next connection. of the second adder device, like this. And this is all done pretty much. Now we have the opposite or symmetrical arrangement, and we can once again try to do a little bit more testing. I'll save this and put this back into the simulation mode, back to our manipulation right here, and let's try some variations. So now when the values are equal, x equals y, you see that both of these are turned off, so they're cleared, and that's nice. So we have an indication of equality right here. But then y becomes greater, and we get the signal of that. But then x keeps growing, and also we get the equality result because these inputs are equal. But if x somehow drops to be less, you see that the device is working very nicely. So I'll put this back to the design mode, stop the simulation, and of course the final step in this design is to indicate that when neither of these two are set, that should be our equality. So let's produce the third signal or something in the middle, and I'll change this annotation to say that these two equal to one another. And of course the output should be derived from two of these signals. So when both of these signals are set to 0, we should get a indicator that is set for us. So if you think about an OR gate, basically is set to 1 only when both of these would be set to 1. But if we use the NOR gate, which inverts the result of OR, that should work for us quite nicely. So I'm thinking that an OR gate right here, if you think an OR gate here, and NOR gate, not OR, should give us a reliable indicator. So let's rearrange this a little bit to have a little bit more space right here, so we can wire it in. And actually, let's place an LED first and wire these connections pretty directly with this NOR gate, and of course these as well. So once again, save it, and if I put this back in the simulation mode, let's try some combination. So right now x is less than y, now x is greater than y, and at this stage let's make them equal. So for example, we change this value, and here we go, we have this result that x equals y. So if we reset all of the inputs to 0, for instance, of course again we get our equality. So I would always try to test these designs and pretty much any other case similar to this with some sort of like boundary values, like all zeros or all ones. So if we set everything equal to 1, let's make sure that our final result is still in place and we can rely on it. So this is the circuit that I would like you to submit for our Lab 5.